I want to talk about something that sort of bothered me about the floor function. And let me just show you a usual concrete example here. Let's look at the floor of, let's say, 21 over 5. Now, if you divide 5 into 21, you get a quotient of 4 and a remainder of 1. Okay, so we'll write down 4 here, and that's what the quotient stands for. 21 is equal to 5 times 4 plus 1. Okay, so that's our floor. And that's just by common, it's our floor. It's the greatest integer that's less than the input argument. Well, 20 over 5 is 4, so this is 4 just by inspection. Okay, now let's take a look at the additive inverse of this guy. That would be minus 21 over 5. Now this is often called, long ago it was called the greatest inner function. It's been supplanted by the term floor, I think, for the most part. But this is actually equal to minus 5 here. And the reason is minus 5 is the greatest integer that is less than this number. Remember, minus 25 over 5 would be negative 5, right? So you actually get this kind of pattern going on. If you have q, the quotient of a positive rational division, then it's going to be, if you turn that to the minus counterpart, it's going to be minus the quantity q plus 1. Now let's get into the proof of it. The division algorithm gives us all we need to know here. We're taking a and b to be positive integers. And in both cases, you get remainders that are less than or equal to the divisor b. Okay, 0, 1, 2. I use this membership notation. I like it. It's a little more explicit, but a lot of people will write this as 0 is less than or equal to r is less than or equal to b minus 1. But in any event, you get these two conditions here by the division algorithm. And I wrote down, definitely I subscripted the quotient here and the quotient and the remainder here because they're going to be different. All right. Now, if you add these two division algorithm equalities, the a and the negative a cancel. That's where the 0 comes from right here. You see the 0 right here? That's a plus negative a gives you this 0. All right, and now we're going to solve this expression for q sub 1. All right, because we're trying to show this part of it. All right, so when you do solve for q sub 1, you get minus q, which is looking close to what we're interested in, but it's plus minus r sub 1 plus r over b. Now, one thing to notice here, we have some constraints on r and r sub 1. This would imply, these two constraints would imply that r sub 1 plus r is less than or equal to 2 times b, 2 times the quantity b minus 1. All right, folks? All right, so this is not even as big as 2b, right? But we need q1 to be an integer. Well, q is known to be an integer, but the only way r1 plus r can be an integer if r1 plus r is equal to b. See, because there's only one multiple of b between 0 and 2b, 2 times b minus 1, namely b itself, right? So this implies right here, just this condition, the fact that integers are closed, this implies that r sub 1 plus r has to equal to b. And I like that because we use two pieces of information here, namely that this entire piece to the right of the equality has to evaluate to an integer. Well, q is already an integer, and the only way that this part can be an integer is if r1 plus r is equal to b, given this condition. This is, we don't see 2b here. B would be the only multiple in this permitted by this inequality. Okay, but what does that tell us? That tells us that this is equal to minus q minus 1, right? r1 plus r is equal to b, minus b over b is minus 1, and this is equal to minus the sum q plus 1 as desired. Okay, so QED time. Okay, QED, and that, again, that is what we're trying to establish. This statement right here implies this statement right here. Division algorithm and just a tiny bit of logic. Fairly straightforward proof, but still a little bit of thought had to go into it. And paying attention to the constraints on the remainders when these divisions are going on. Okay? All right. All right, y'all. Thank you for viewing.